Welcome. In this video, we are going to take a look at graphs, surfaces, and cross-sections. One of the things we've already done in our prior lesson is that we've already made the connection between two-dimensional graphs of multivariable functions. And the way we did that is we held something constant, and we drew for each of those constants of that one input variable, we drew two-dimensional graphs of the resulting input variable with the output variable z. And so then we kind of telescoped those and realized that if I have a bunch of two-dimensional graphs, here, and each one of these just represents a different value of the constant, then what I can do is kind of telescope those out so that one line's here, one line's here, and one line's here, and now I start to see sort of this pattern in this three-dimensional function, or this shape of the corresponding graph. And what we're going to do now is take a look at algebraic functions, so situations where a function is defined by an algebraic expression. So how do we identify a graph? For instance, which one of these below is most likely going to be the graph of z equals x squared plus y squared? So I have two graphs, and I see that one almost looks like what I would call maybe a parabola in 3 dimensions. This guy actually has the name paraboloid, because it does look like a parabola, but just in sort of what you would imagine to be 3 dimensions. Now this graph down here has some interesting features in it. First of all, I sort of see this almost periodic function going on here, and then depending on which perspective I look at it in, if I look at it from sort of going left to right, in this direction here, what I see is that oscillating function. And when I look at it in the other direction, going this way, what I see is actually, if I were to look at it from that angle, or if I were able to rotate this graph so that this edge is facing us, then what I would see is a parabola. So in one direction, I sort of see a periodic, and in the other direction, I see a parabola. Now we know that periodic functions are going to be your typical, usually your sine and your cosine functions. So this function right here, x squared plus y squared, doesn't seem to have anything that would indicate oscillations over either x or y. Now one of the things that I could do, of course, is I could create a table, and I could just say, let me put my x and my y values along the horizontal and vertical, and maybe just look at different values of x, like we'll just say -1, 0, and 1, and look at the values of y as -1, 0, and 1. So from the function, I could actually build the corresponding z values for these individual pairs. So if x is -1 and y is -1, the square of -1 plus the square of -1 is going to be 2. If I look at x is -1 but y is 0, -1 squared is 1 plus 0 squared is 1. And then same thing here, I'll have 2 because the square of -1 and the square of +1 added together. And when x is 0 and y is -1, we'll get 1. When x is 0, y is 0, we'll get 0. X is 0, y is 1, we'll get 1, and kind of a similar pattern here. Here we'll have, this should be 2, and 1 squared plus 0 squared is going to be 1, and 1 squared plus 1 squared is going to be 2. So what we should kind of see is we have a low spot here. If I could kind of imagine coming out at us from the screen for each of these grid values, if I had a bar, a bar basically coming out from this little area here and kind of coming at you, it would have a height of 2 units. But over here, this little rectangle would have a bar that would come out into the screen a distance of only 1 unit. And same thing here, this one would be a really high point, and we could kind of shade these different colors if we really wanted to get to look at elevation. So if I used if I used something a little bit darker, like these are kind of the higher points here, and then if I used some of these are a little bit lower, and right in the center I have my lowest point, which has a height of 0. So we can actually see that this graph should go through the point x is 0, y is 0, z is 0. And that is, in fact, what this point looks like right there. That is x is the red axis, y is the green axis, and z is my vertical axis. And so that does seem to have the point 0, 0, 0 on it. Now this graph over here, if we look at this very carefully, it's kind of hard to tell. It looks like it might go through 0, 0, 0. But since we are looking at a three-dimensional surface and we can't rotate this one, it's a little bit difficult to tell. But here's the interesting part. If I do just hold one of the variables constant, for instance, if we say, let's have x be held constant at -1. Or better yet, let's start with y. Let's say we held y constant at -1. Okay, so this graph is going to be a graph of z versus x when y is -1. So in terms of where my table indicates y being held constant at -1, that is this column right here. So what I want to plot is the corresponding ordered pair x and z. When x is -1, z is going to be +2. When x is 0, z is going to be +1. And finally, when x is 1, z is going to be +2. So if I continued to draw these points, what I would notice is that we have a parabolic shape for when y equals -1. When y equals 0, if we looked at that cross section, as we'll call them soon, we'll define these to be cross sections. And now I take a look at the plot between z and x. So here I have my z-axis and my x-axis. But when y is being held equal to 0, now when x is -1, my z value is +1. And when x is 0, z is 0. And when x is 1, z is +1. So you can see we have another parabola, but that parabola looks to be shifted down 1 unit in comparison to this parabola over here. And I could do the same thing for y equals +1. And for y equals +1, if we plot z versus x, well, that's going to be the third column. Y is equal to 1. And so now I'll be looking at when x is -1, z is 2. X is -1, z is 2. When x is 0, z is 1. And when x is 1, z is 2. So it looks like the connection between these is that as we move from y equals -1 to y equals 1, we get something that from here to here shifts down 1 unit. But then from here to here, the graph shifts back up 1 unit. So if we imagine what that might look like, well, where is y equals -1 on this graph? That's going to be back here. So if what I do is I fix my y value to be -1 and I look at the corresponding graph, what I should see is a parabola that is lifted off. I'm trying my best here to draw this perspective, and I'm clearly not very good at it. So let's see, maybe more like this, we'll just say. So that parabola that we see there corresponds to y equals -1. Now when y is set equal to 0, that's everywhere where y is equal to 0, what I get is a parabola that starts down at the origin and looks like this. So all I've really done here is I've basically taken what we call a cross-section of this three-dimensional function. We could do the same thing for y equals 1, and I should notice that same parabola that's shifted up 1 unit. And I apologize, I know my sketching is not real great here, but I hope that you're able to see the connection that basically what we're doing here is we're just slicing we're slicing this graph at y equals -1, and then taking a look at what that slice looks like if we were to create that slice going all the way across like this. So if we were to slice that graph and we were just to look at the imprint on that two-dimensional platform right there, then what we would see is a parabolic function that is shifted up 1 unit. So again, we would see something like that stamped on there. And that's basically just this window right here. We're projecting that three-dimensional graph onto a two-dimensional surface. Now, also algebraically, another thing that we could have done with these three graphs is instead of looking at the relationship between x and z when y is -1, we could have taken a look at the relationship between y and z when x is -1. So when x is -1, we're looking at this graph here. And you can see that that's going to have the same for that value of x when x is -1. I'm sorry, when y is -1, z is 2. So instead of labeling this z and x, we would label this z versus y when x is set -1. So we actually get the exact same graph by looking at holding a value of x constant and altering the value of y. Another way of thinking about this, instead of looking at ordered pairs, is we could say, well, if we hold y equals -1 constant, we could do that in the function itself. We could say, well, f of x and y is being held constant at -1. The function is x squared plus y squared, and that produces the graph of x squared plus 1. So in other words, if I hold y constant at -1, what I should see is the graph of the function x squared plus 1. Well, this is the parabola x squared that is shifted up 1 unit from the origin. And when y is -2, we see that f of x comma -2 is equal to the graph x squared plus -2 squared, which is x squared plus 4. So if I had used y as -2, then this function would have been shifted up 3 more units. And also we could do y is equal to 0 and see that that's just going to be another parabola, f of x comma 0. That will be the graph of just x squared, which is the parabola that has its vertex at the origin and looks like that. And guess what? That's precisely the graph that we've started to sketch out here for when y is equal to 0. Now, in general, if I held y equals c, so just pretend that this is some number, then what I'm going to get is x squared plus some constant squared. And we can see that this is always a parabola. And we could do the exact same thing for holding x constant. If x is equal to some fixed value, x equals -1, then f of x comma y will give me the graph of -1 squared plus y squared, which is equal to y squared plus 1. Now we have to remember that this is z, that f of xy is just another name for z. So when I go to graph this function, my output variable is called z, my input variable is called y, and this is going to be shifted up 1 unit in a parabola that looks like this. So if whether I hold x or y constant, if we now just say hold x equal to some constant value, then the graph that I get is that of a parabola that's going to look like this, y squared plus constant squared, which you notice is very similar to this graph up here, other than our input variable is called y instead of x. Don't let that confuse you. It just means that one of the axes is called the y-axis, even though it's not the same as what you would normally think of as the y-axis in an algebra class. And so this is still a parabola. So what this means is that regardless of whether I'm looking at holding, for instance, if I look at the graph going this way, if I were to rotate this graph so that that line is parallel to the screen, then what I would see is these parabolic cross sections, these sections that are parabolic going this way. And if I were to look at the graph dead on, looking down, scoping down the y-axis this way, what I would see is a parabolic graph as well. Except that blue parabola is what we would see when we would look that way, and this pink parabola is the parabola that we would see when we would be looking this way. So we've justified in a number of ways that this surface corresponds to the graph x squared plus y squared. It's a parabola in both the x and the y directions. In this case, what we want to answer next is what would be a reasonable function for the graph you did not choose to represent f of xy equals x squared plus y squared. So here, when we're taking on this view, what we're looking at is this is the x-axis, and if we scoped down the x-axis, what we would be seeing is the graph of z versus y. So again, we're holding the value of x constant, and when we do that, we just, regardless of where we create this cut, whether we look at it here, you can actually see that that wireframe right there, that's the same sinusoidal function, that just seems to be elevated up. So that must be for a value of x that is closer in this direction. I know it's kind of hard to visualize. We'll soon take a look at an applet that gives us a better sense of visualization. The reason we spend all this time developing these functions and trying to understand how we graph them is so that eventually we could just look at the algebraic function and not have to be limited by our need to see something on a graph, but to be able to think about it algebraically. So here are kind of the facts. We know that whenever we look at the graph of z versus y, so once again, what that means is that we're looking at the green axis and the blue axes, and we're fixing a value of x. What we see is something that looks sinusoidal. Now again, I can't really tell super well by the way that this angle is rotated, but I'm just going to assume that this parabola intersects the origin right there. So what I'm seeing is kind of something that looks like this. And so this could be the graph of, let's see, well, it kind of looks like sine would do something more like this. So this looks to be something like maybe negative sine. So I'm going to say that this graph to me just visually looks like when x is held constant, we get something that has the negative sign of y in it. And it all depends on x, what the value of x is, to tell us what the remaining piece will be, but it'll be sort of like a sine function plus some vertical shift depending on what value of x we have. I also know that if I looked at the graph of z versus x, okay, so what that's going to be is now we're looking at this red axis. If I scope down the y-axis and hold it constant, what I should see is something that looks parabolic. So that means that when y is being held constant, so I'm just going to put a box there to say that it's being held constant, I see something that looks like a parabola with respect to x. So if I put these two pieces together, I'm going to say, you know, z, which is the same thing as writing f of xy, looks to be something along the lines of x squared minus sine of y. Now it's kind of hard to come up with these functions, but the point is that we see something that's parabolic from one looking down again. So imagine that this right here, that coming out at you is the y-axis, and in this graph here, imagine that the x-axis is coming out at you. So it's almost like we'd see a third axis that goes this way. Okay, so what we've defined here is called a cross-section of a graph. A cross-section of a multivariable function, z equals f of xy, is the function we get when we hold x constant and let only y and z covary. This is the cross-section of z with respect to y. If we hold y constant and let x and z covary, then this is the cross-section of z with respect to x. So if what we're looking at is z versus x, this is the cross-section of z versus x. And if we look at z versus y, then that's the cross-section of z versus y. All right. And we'll go ahead and take a look at this nice little applet that'll help us visualize these cross-sections. So in this applet, we can type in a function here. Right now it's set by default to x squared plus y squared. And you can rotate this and you can see that, hey, that's the same graph that we were working on identifying. And now you can kind of see what I'm talking about with respect to looking at the axes. If I rotate this so that the x-axis is coming directly out at me, and I'm looking at the cross-section of z versus y, you can just tell from the outline of that shape that that's going to be parabolic. Now, on the other hand, if I rotate it the other way so that the y-axis is coming out directly at me, like about so, close enough, then also what I see is a parabolic cross-section. Now, what we can do with these sliders is we can fix the value of either x, y, or later on we'll look at fixing the value of z. But if I look at, for example, x equals, let's say, 0, if I hold x constant at 0, what that means is that when x is 0, that's on this red line where on the red line we have a marker of 0, and we see this blue shape. That's what we would get if we took a slice, if we took a knife and just sliced this thing down at x equals 0, we would see this purple or bluish looking parabola that would be the resulting shape if you slice this thing down this way and split it into two halves and then looked at the shape that those two halves created at the seam. If I set x equal to 1, then you can see that we get the function x equals, or z equals y squared plus 1. And now that's just the parabola that if we were to slice this paraboloid at x equals 1 right here and then split the two pieces apart, where they connect at that seam forms a parabola that's elevated 1 unit above the xy plane. And when x is 2, you can see that that's just going to be the same thing, parabola that's lifted up 4 units because y squared plus 2 squared gives you that parabola. And same thing goes for when x is negative 2, because we are just squaring that value. That will also be a parabola elevated 2 units above. So the trick to understanding three-dimensional functions is to reduce the three-dimensional function into two-dimensional pieces. Now when I do this for the y value, I get the same type of result. This is when y is about negative 2, or pretty close. You see we get the graph of x squared plus 4. So that graph right there, when we zone out that axis, that y-axis, then we get the graph of x squared plus 4. If we start to change that closer to 0, well, that parabola is just going to shift closer to having its vertex at the origin. You can see there we are right at the origin. There's the graph of z equals x squared. This is the z-axis and the x-axis. And when we make that positive, it's just going to rise in the other direction, because the larger the number that we square, the more that parabola will be shifted off the surface. We'll come back to what the value of z does in a separate lesson. Okay, so now that we have a sense of what that looks like, let's see what we would describe a graph without seeing it, what kind of features we would expect this to have. So let's think about the graph of f of xy equals x squared. Now you see that this doesn't have a y value in it. If you do, however, write this as f of xy equals x squared plus 0 y, then it's as if there is a y variable in the equation. It's just being multiplied by 0, and therefore it will not have any impact on the value of y will not have any impact on the shape of the graph. So if I look at this for different values, for instance, if I first of all start by looking at z versus x for when y is, say, -1, well, again, the value of y does not affect the shape of the graph, so this function will simply be z equals x squared, which is the parabola. It looks like that. Now, if I scoot in closer to y equals 0, and I take a look at that resulting two-dimensional graph, well, again, the value of y doesn't affect the relationship between z and x, so that will be the exact same parabola that we had over to the left. So completely unaltered. When y equals +1, same story, the graph of z versus x still remains z equals x squared, because the value of y does not affect the graph. So if we then tried to take these three pieces and we tried to pretend that this was the value of, let's say the value of y here, I'm going to put the value of x here, so to make it a little bit easier to look at. So here's the negative values of y. Here's y equals +1. When y equals +1, I get the parabola z equals x squared. When y is equal to 0, I get the parabola y is equal to, or z is equal to x squared. And when y is -1, I get the exact same parabola again. So it's almost like we have a bunch of parabolas that are just the same height and just stacked together, almost forming what looks like a half pipe, a ramp of some sort. I'm seeing something that looks kind of like this. Well, that's a very bad illustration, but let me see if I can take this piece here and move it over a bit. There we go. That's going to look a little bit better. And now we have something that looks a little like that. So let's take a look at the cross-section of this just to confirm our suspicions. Oh, and another thing that we should note is that when we hold x constant, if x is equal to, say, -1, then the graph that we get is f of -1 comma y. Well, again, the y value does not influence this graph at all. When we square x, though, we just get 1. So that means that if I draw the relationship between z and y, I get the graph of the function 1, which is just a horizontal line at z equals 1. If I look at f of 0 comma y, I get the graph 0, which is the same horizontal line, just shifted down 1 unit. And same thing with when I have x equals +1, then I'm going to get this graph shifted up 1 unit. So let's take a look at it. We'll just take a look at the graph of x squared. And here's exactly what we're seeing. This is the relationship of, well, first of all, there's the parabolic functions we have. That's when we're holding y constant. And when we're holding x constant, it's a little bit harder to see, but there are straight lines that we see from left to right, depending on what value of x we are fixed at. So here is just me changing the value of y. You see that it does not change the shape of the graph at all. It's still the function f of x equals x squared. Again, the value of y does not influence that parabola. And then if I look at the value of x being fixed, you can see why we see those straight lines now. That's a straight line going all the way across. If I slice this the surface going this way, and I split those two pieces apart, the seam would be a straight line. And again, it's going to be a straight line regardless of where I split it in this direction. Interesting stuff. So the other function here, f of xy equals x squared minus y squared. Let's see if we could do this a little bit of justice just by thinking about holding y constant. So if I hold y constant at y equals c, f of xc will be the graph x squared minus c squared. Now this right here is just some number, some constant. So that's going to be a parabola that's shifted down c squared units. Parabola. So if c was 1, then this would be the parabola x squared minus 1. X squared minus 1. This is for y equals 1. if y were to equal 0, then it would be just the parabola z equals x squared. And if I hold x constant, the graph that I would get is f of c, so let's just say we hold it constant, c comma y is equal to c squared minus y squared, which is the graph negative y squared plus c squared. Now, this is a parabola, but it's a parabola that opens downwards. So this is going to have the general shape of pointing downwards like this. So in one direction, when we look at this graph, we see parabolas opening upwards, but then when we rotate that graph to look at z versus y, we see parabolas that open downwards. So how do we put these two things together? Well, it'll become readily apparent when we do it in here. We type in minus y squared and graph that. You see that in one direction, I'm going to zoom out a bit. You can see that in one direction, when I look at it there, I see parabolas. This is when I'm holding the value of y constant. You can see that we just get parabolas that are shifted lower. There's when y is equal to 0. We just get the graph of z equals x squared. But if x becomes positive, that parabola gets shifted down because it's a minus sign. And if we make x negative or y negative, then we still get a minus sign there because we're squaring the value of y. However, when I take a look at this graph from the y perspective, that is, we cancel out, we hold the value of x constant, then the graph that we're seeing is actually a set of parabolas that face downwards, and you can see that depending on how big or small that z value is, if z is really negative, it's a parabola that's shifted high but facing down, and then here we are at around y equals 0, and here we are at positive y values. So we kind of get this saddle looking thing. It kind of looks a little bit like a saddle, and it's kind of like the horse's saddle. It opens upwards in this direction, but opens downwards in this other direction. So now that we have a better sense of how we can understand multivariable functions, given the algebraic expression for that function, we can now start to study some applications and think about how does this thinking allow us to understand real-world relationships. In this example, consider the concentration, C in milligrams per liter, of a drug in the blood. So basically this is going to be, and usually concentrations are measured as mass per volume. So here it's how many milligrams of this drug we have per liter of blood in our body as a function of X, the amount of the drug given. So, well, first of all, your blood concentration of that drug depends on how much of it has been administered, as well as how long it's been in hours in the bloodstream. So to figure out how much of this drug you have, we need to know how much of it you were given, but we also need to know how long that drug has been in your body. Because of course, if you took aspirin 2 weeks ago, even though you may have taken a large dose, because it's been 2 weeks, that's probably going to result in a lower concentration. So as t goes up, we would expect the concentration to go down. But in terms of that's if we're holding the initial dosage at a fixed level. But as we increase the initial amount that we've taken and we hold time constant, well, that's going to increase our blood concentration. So that's probably intuitively what we should see as we begin to analyze this. So find f of 3, 2, give units, and interpret in terms of drug concentration. So f of 3, 2 requires us to hold x at a value of 3 and t at a value of 2. So it's going to look something like this. This will be 5 minus 3. And we can approximate this with our calculator, which gives us about 2 decimal places, 0.04. So we have to think about what components we plugged in here. X, was how many initial milligrams we took. 2, that was how many hours had passed. Hours passed since 3 milligrams taken. Or so we can say 2 hours passed since 3 milligrams taken. And then finally, this output that we get from this function, this output represents the concentration, which is 0.04 milligrams per liter in the blood after having taken 3 milligrams 2 hours ago. Okay, and of course whether that's high or low just depends on what kind of drug it is. So of course different drugs are going to have different doses, so we can't really comment on whether this is high or low. For aspirin, this would obviously be very low, but for other drugs it may be very high. Okay, so we kind of want to understand again this relationship. Here intuitively we've said that if we were to ignore time or to hold it constant, the higher the initial x is, the higher that concentration will be. However, if we hold the dosage constant and we look at the relationship between concentration and time, we would expect that as time passes, the concentration drops. So for graph number 1, we want to look at f of 4 comma t. So this means that we're going to take 4 milligrams, and we want to look at the resulting graph between the concentration and the amount of time that has passed. So first of all, I have to think about what this function is. This is when I substitute 4 in for x, and since my function is te to the negative t times 5 minus x, 5 minus x will be 1, and this will simply be t times e to the negative t. So to take a look at this graph, let's go ahead and plot it in Desmos to make our lives a little bit easier. And here's the graph that I get when I plot x e to the negative x. So my concentration axis and the amount of time that has passed. So I see, first of all, at time 0, I have nothing in my bloodstream. That means I haven't taken the medication yet. Then I've swallowed the medication. And so over the course of the first hour, I actually achieve a maximum concentration of 0.368 milligrams per liter after 1 hour. So it takes about 1 hour for that drug to get into my bloodstream. And over time, from there, the amount of that drug in my bloodstream will decay back down to 0. Initially, decays kind of rapidly, but then it starts to flatten out. So we can go ahead and plot something that looks like that. We can say that, all right, well, it starts off at 0, and then at time 1, it hits that 0.368. So here is our time 1, and this is going to be at 0.368. And so what we can say is that the dosage spikes concentration at time 1, and I won't write this out, but what we would want to say is that at first when you take that medication, the concentration of that drug in your bloodstream increases gradually over the course of the first hour, and then after the first hour, it slowly loses its effectiveness. So it seems like a pretty realistic model so far. Here we're going to look at the 1 hour mark. Now we already kind of know what's significant about the 1 hour mark for this graph. That was when we had an initial dose of 4 milligrams, and the graph, we noticed the blood concentration spiked at time 1. What we could also do is just sort of simulate to see if that would be the case for any initial dosage taken. So what I can do here in Desmos is I know that this is negative x times 5 minus x, negative t times 5 minus x. So what I'll do here is I will put times 5 minus, and then I'll just say, I can't use x again, unfortunately. I can't use t in this editor, so I will just say that this is d for dose. So this is a dose of 1 milligram. and it doesn't seem to be consistent. Here's that dose of 4 milligrams. So that spiked after 1 hour, but it looks like if I take a lower dosage, like 3 milligrams, then it only takes about a half an hour for the blood concentration to spike. And so it seems as I take lower dosages, that concentration spikes in my bloodstream much earlier, but if I take much higher concentrations, then for example at 4.5 milligrams, it takes 2 hours to spike, and it's about double the concentration that I achieved earlier. So maybe that wasn't a valid justification that time 1 is significant in that sense, but that's okay because sometimes exploring these leads us to greater conclusions. When we just learned that when your blood concentration spikes is a function of how much you took because it takes your body time to process. And here we have when t is equal to 1. So if t is equal to 1, that means I'm going to have the graph 1e to the negative 1 times 5 minus x. And so now I'll go ahead and take a look at that graph. So that will be the graph of concentration versus the initial dosage taken after t equals 1 hour. Okay, so this is kind of a weird graph to look at because what we're doing is we're looking at what the blood concentration is after 1 hour based on your initial dosage. And so what I'll do in here is I will just change this to e to the negative 5 minus x. And what we see is that there's an exponential relationship between concentration and the amount of time, and the initial dosage that you took after 1 hour. So if you've taken a really high dosage after 1 hour, that concentration will be much higher than if you only took a low dosage of 4 milligrams after 1 hour. That blood concentration would be a lot lower. And that kind of makes sense too, because after 1 hour, we would expect higher initial dosages to have higher concentrations at t equals 1 hour. Then the same thing for the lower ones. Now what's interesting here is that even though your concentration, your initial dosage is only increasing by 1 milligram, an extra 1 milligram actually creates a massive spike in your blood concentration after 1 hour in comparison to taking 1 milligram less. So what we'd see here is something that looks like this. So again, we could just say something along the lines of higher initial dosages will lead to higher blood concentrations after 1 hour than lower ones. And so now you can see that analyzing things as cross-sections can reveal a lot of information about that context. The last thing that I'd just like to propose here is just these are some different common functions that we run into in three-dimensional space. And a lot of these will kind of remind you of things maybe you've seen before. So we defined a paraboloid as z equals x squared plus y squared. But you can actually make this an elliptical paraboloid where maybe it's hard to see here, but maybe it's wider in one direction and kind of narrower in the other. So basically from the top, if you looked at this graph from the top, you would see more of an elliptical shape in certain cases. You know, there's no reason why I couldn't see a really wide parabola in one direction and it's really narrow here in the other direction. You get this hyperbolic function. Notice that this has a negative here, and that was the one where we saw something that looked kind of like a saddle. Because of that minus, in one direction we have a parabola that opens down, in the other direction a parabola that opens up. One of my favorites is the ellipsoid. If A, B, and C are all 1, then you get what's called a sphere. Sphere if A and B and C are all equal to the value of 1. And that should kind of make sense because if we remember that x squared plus y squared equals radius squared, that would give you a circle in x and y of radius r. So now just adding that third variable in there and constricting them all to be equal to 1. Now that's going to give you a radius of 1. In general, this could be r squared, and whatever that number is, its square root will represent the radius. Some other common ones to toy with are these ones, the hyperboloid, hyperboloid of two sheets, cone. These are sometimes things we run into. But I'd like to really focus on these. We'll study planes in one of our next lessons. And then you have these cylindrical ones. And I want to spend just a moment on this guy here. Why does this look like a perfect cylinder? The same circle going up and down. Well, notice that this equation only relies on x and y. So in the next lesson, when we focus on contours, we can also hold the value of z constant. So if z equals, say, -1, so that's going to be down here at -1, and that's going to be mainly focusing on the stamp of this cross-section right there, what I should still see is the graph of x squared plus y squared equals a squared, where a is really just the radius. So I'll see a circle of radius a. Now when z is equal to 0, well, z does not come into play in this equation, so the equation is still x squared plus y squared equals a squared, which means I have a circle of radius a. So regardless of what value of z I'm at, I am going to get the exact same circle. And therefore, at all of these different values of z, whether I slice it here or I slice it up here, what I'm going to see is the imprint of a circle on that xy plane. So if I hold z constant, what I should see is the relationship between the x-axis and the y-axis is a circle. Again, same thing here. And you can also reason through this one. Doesn't matter what the value of z is, the relationship between y and x is a parabolic one. So if z is -1, I get a parabola between the x and the y axes. And an easier way to draw this would be to have the y and the x going this way. And then there's that parabola. It just happens to be laying on its side because the y and x axes are laying on their side as well. So there are many, many, many different multivariable functions out there, but again, the core skills that we've learned here are to think about cross-sections by holding one of the variables physically, by holding it constant within our equation.